This presentation will allow you to come up with a preliminary design for distilling a binary mixture to meet some target specifications. We're going to use a technique called McCabe-Thiele graphical method, and this will allow us to do stage-by-stage mass balances in a distillation column. It will also allow us to determine the number of stages needed for a column design to meet the specifications required for the project. Also allow us to determine the location of the feed stage and understand minimum reflux ratio. In this diagram, we will see a generic column where we have some feed entering a column at feed stage labeled F. And in the binary mixture, our feed composition has some mole fraction Z sub F. At the top of the column is a condenser where the vapor from the top of the column is condensed into a liquid, and a portion of that liquid is returned back to the column as reflux, and the distillate is also taken off at the condenser with the product D and containing the mole fraction X sub D. At the bottom of our column is our reboiler where the bottom stream is taken off and it has a composition X sub B. We'll take advantage of, with a binary mixture, doing two material balances, one being a total balance where the feed F is equal to the distillate plus the bottoms, and then looking at our one component, the mole fraction of it in the feed times the feed flow will equal the distillate mole fraction times the distillate flow, and the bottoms mole fraction times the bottoms flow. The first thing we're going to do is design the column above the feed stage. And here we'll look at vapor stream coming from stage 3, which we labeled V3, with a mole fraction in the vapor phase Y3, entering the bottom of stage 2. And this vapor then passes through stage 2 where it is in contact with the liquid coming down from stage 1, labeled L1, with a mole fraction X1. The streams leave as L2 and V2, and the vapor stream coming from stage number 2 enters stage number 1, where it is mixed with a liquid coming from the condenser known as the reflux. And this reflux has a flow rate of L0, and it also has the same composition of the distillate mole fraction X sub D. And we're going to define a reflux ratio labeled R as the ratio of this return stream, the reflux L0, divided by the distillate flow. Now let's do a material balance around stage 1. Entering stage 1, we have a vapor V2, composition Y2. We also have leaving stage 1, a liquid L1 with composition X1, and our distillate product D with composition X sub D. And we can do a component material balance around this where the mole fraction from stage 2 times the vapor stream stage 2 is equal to the distillate mole fraction times the distillate flow plus the liquid L1 times the mole fraction X1 will be a component balance. But note that the stream leaving stage 1 in the liquid phase is in equilibrium with the stream leaving stage 1 in the vapor phase. Therefore, X1 is in equilibrium with Y1, and Y1 is simply equal to the distillate mole fraction X sub D. Carrying on the material balance, we have the component balance. And also note that the vapor stream leaving the first stage will equal the liquid stream that is returned as reflux, L, plus the distillate. Now we're going to make an assumption here that will allow this method to be used very elegantly. We're going to assume that the vapor above the feed stage, no matter which stage it is relatively constant throughout the column. And we'll call that as flow rate of V. Likewise, the liquid coming down from the top of the column to just above the feed stage will be relatively constant as well, and we'll call that L. And this is known as the equimolar overflow assumption. So now we will substitute V for V1 and L for L1. And our material balance equation for the component at around the first stage, we'll have Y2 times V. That will equal XD times the distillate flow D, plus X1 times the liquid flow L1 that's being refluxed back into column. And we'll make a substitution that the vapor leaving stage 1 is equal to L plus D, and put that into the equation. Divide by the distillate flow D, and we end up with an equation that the mole fraction leaving the second stage in the vapor phase is equal to the distillate mole fraction divided by the reflux ratio R plus 1 plus the mole fraction X1 in the liquid phase from stage 1 times the reflux ratio divided by R plus 1. Note that this is an equation of a straight line with the intercept equal to XD over R plus 1 and the slope equal to R over R plus 1. Now we're going to look at how to solve this problem in determining the number of stages above the feed stage graphically. On our graph here we have two lines, one being the y equals x line, and the second is a suitable vapor-liquid equilibrium curve. The one you see in front of you was generated using Raoult's law. However, different models are available depending on the nature of the liquids and vapors in equilibrium with each other. Looking up at the diagram at the top, we see that Y1 going out of stage 1 goes through a condenser and is condensed to a liquid. It will have the same composition as XD. So we can find that on our Y equals X curve, and it is located about mole fraction of 0.95. Now look at the diagram at the top and you'll see that X1 leaving stage 1 is in equilibrium with Y1 leaving stage 1. And so its composition can be found at the point where Y1 is located on the equilibrium curve. And so X1 can be found, and it's about a value of about 0.83 taken from there. Now we're going to add a third line to our graph. This is called the operating line, and it's generated by using the material balance equation around stage 1. Here we have this equation, y sub 2 is equal to the distillate mole fraction xd over r plus 1 plus reflux ratio r over r plus 1 times x1. This is an equation of a straight line. The y-intercept is given to us when x1 is equal to 0, and it's just xd over r plus 1. In our diagram, the y-intercept is about 0.32. This line will also intersect the y versus equals x curve when x1 is equal to xd. So this now is our operating line, which we will use for the design of our column above the feed stage. We know x sub 1 from our equilibrium curve, so we can determine y sub 2 by dropping that value straight down to the operating line which we generated. Now that y2 is found from our operating line, we can look at our second stage and note that x2 is in equilibrium with y2. Therefore, we take the value y2 and project it into our equilibrium curve, and this will determine what x2 is. Now, y3 from our material balance can be given by our material balance, which we call our operating line. So we project x2 down to the operating line, and this will determine y3. Now that y3 is determined from the operating line, x3 can be determined from the equilibrium curve. And now that x3 is known, we can determine Y4 by looking at the material balance and using the operating line equation, substituting in the value for X3. And this procedure can be repeated above the feed stage until we get to the feed composition. Now we'll take a look at below the feed stage. Here we have a reboiler where vapor is generated. Our bottom flow rate is labeled B and has a composition of X sub B. And we have vapor rising up the column and liquid coming down the column. We're going to do the same type of assumption as we did before, where the vapor leaving each stage rising up is relatively equal to the one from the previous stage, and we'll call that V prime. Also, we will assume that the liquid coming down from each stage is relatively constant, and we'll call that L. This is also known as the equal molar overflow assumption. Note that in this particular design, Y sub B is the composition of the vapor stream leaving the reboiler, and since we have two phases mixed together in equilibrium, YB will also be in equilibrium with XB. Now we'll do a material balance around the reboiler. In this case, we have a liquid stream coming down, which is L prime, and that has a composition of X sub N. And leaving the reboiler, we have two streams. One is the vapor stream V prime and has a composition YB, and also a liquid stream leaving the reboiler labeled B and has a composition of X sub B. We're going to define another ratio concept called the boil-up ratio, and that's just the ratio of the vapor divided by the bottom's flow, and we'll call that R sub B. Substituting that into our material balance equation, we have X sub N times V prime plus B will equal Y sub B times V prime plus X sub B times B. Substituting in by dividing by the bottom's flow B, we have X sub N times RB plus 1, and that will equal the YB times RB plus X sub B. And we have finally Y sub B times X sub N multiplied by RB plus 1 over RB minus X sub B over RB. Notice that this is an equation of a straight line. It has an intercept of negative X sub B over RB and has a slope of RB plus 1 divided by RB. I can now do a similar graphical stepping off like we did above the feed stage. Coming out of the bottom of the reboiler, we have X sub B, and we know that Y sub B, the vapor leaving the reboiler, is in equilibrium, so we can find that point on our equilibrium curve. Using our material balance equations, we can plot the operating line below the feed stage using the equation we discussed earlier. And knowing Y sub B, I can find out what the value of X sub N is by projecting that value Y sub B to the operating line. Now X sub N is now known. Since Y sub N is in equilibrium with X sub N, I can determine that from the equilibrium curve. I now shift over to the operating curve to find out what the value of X sub N minus 1 will be, and then project that up to the equilibrium curve and determine what Y sub N minus 1 is. And this procedure is repeated until we reach the feed stage. Now that we've studied the operating lines above and below the feed stage and how to count off stages, now we're going to focus our attention at the feed stage. Here we are introducing our feed, which has a composition Z sub F. Above the feed stage, stage F minus 1, we have a liquid coming down with mole fraction X F minus 1. From below, we have a vapor coming up, and it has a mole fraction Y F plus 1. leaving stage F, we have a vapor, V, with a composition YF, and a liquid L prime, which has a composition XF. And as before, the liquid and vapor streams leaving the stage will be in equilibrium with each other. Now we're going to perform simultaneous mass and energy balances around the feed stage. For total flow, we have the feed F coming in, the vapor coming in from the bottom, V prime, liquid coming in from the top, L, and that will equal the vapor V and liquid L prime leaving. That's our mass balance. Our energy balance, we would take those same streams and multiply it by the specific enthalpy of those streams. Now we're going to make an assumption. We're going to say that the specific enthalpy going from stage to stage is relatively constant. So for liquid enthalpy, the enthalpy of the liquid at leaving stage F is approximately equal to the liquid coming down from stage F minus 1, and we'll call that H sub L. And we'll do a similar procedure with the gas phase enthalpy H sub G. We'll substitute those values into our energy balance equation, and after a little bit of manipulation, we find that we can ultimately get down to a point at the bottom of our slide where the specific enthalpy of the gas minus the enthalpy of the feed divided by the enthalpy of the gas minus the enthalpy of the liquid will be equal to L prime minus L over F, and we're going to call that a variable called Q, and we'll see how that's used in a later slide. We're now going to look at this Q a little more closely to understand exactly what it means. In our stages, the enthalpy of the gas and the enthalpy of the liquid will be at their dew point and bubble point temperatures respectively. If our feed is a liquid at its bubble point, then the enthalpy of the feed will be approximately that of equal to the enthalpy of the liquid flowing in the column. Putting in that value, we will find that Q is equal to 1. Alternatively, if the feed is a vapor at its dew point temperature, then its enthalpy is going to be approximately equal to that of the gas inside the column, and that value would have a Q equal to 0. If our feed is a liquid below the bubble point temperature, then H sub F would be less than H sub L, and if we put that into our equation for Q, we will find that Q would have a number greater than 1. Also, if the feed is a vapor above the dew point temperature, then H sub F would be greater than H sub G, and therefore Q would have a value less than 0. Finally, we're going to do a component balance at the feed stage. Here Z sub F is the concentration and or mole fraction of our feed times the total feed flow, and then that will be added to the liquid phase of our component, X sub F minus 1 times L, the vapor phase, Y sub F plus 1 times V prime, and that will equal Y sub F times V plus X sub F times L prime. Similar to the enthalpy assumption, we'll say that the composition between stages does not change appreciably. Therefore, X sub F minus 1 is approximately equal to XF, and we'll call that X. And Y of F plus 1 is approximately equal to Y sub F, and we'll call that Y. We'll then substitute those values into our equations, and with a little manipulation and algebra, we finally get down to Y will be equal to Q over Q minus 1 times X minus Z sub F over Q minus 1. Again, this is an equation of a straight line with a slope of Q over Q minus 1 and an intercept of negative ZF over Q minus 1. Let's see what happens to our Q-line equation for different values of Q. Let's say that Q is equal to 0, which is a feed that's a vapor right at its dew point temperature. Substituting that into our Q line equation, we will find that y will ultimately equal z sub f. So y is a constant value equal to z sub f when Q is equal to 0. If Q is equal to 1, or a liquid at its bubble point temperature, we will find that y would equal infinity, or y would have a vertical line from the value z sub f. Let's look at our diagram when Q is equal to 0. Here we will use the value y is equal to z sub f, which intersects our y equals x curve at the feed concentration. If our feed is actually at 0.5, then we would draw a vertical line up to the y equals x, and then a horizontal line, which also give us y is equal to 0.5. Now, note that the upper operating line, the Q line, and the lower operating line must all intersect at that one point designated in the diagram. If our feed is actually a liquid at its bubble point temperature, our Q line is a vertical line running through z sub f. And again, our upper operating line, lower operating line must intersect the Q line at z sub f. Next, we will look at a design of a distillation column. We start off with our equilibrium curve, and we have our Q line from our feed curve. In this case, the feed is 100% vapor, and it has a composition ZF, which is a 0.5 on our diagram. So we would take a vertical line at x equals ZF up to the y equals x curve, and then horizontally over to the y equals 0.5. We will then select our upper operating line, which intersects the y equals x line at xd, and then we can choose the slope whatever we wish, but it will point where it intersects the Q line. That point we would then draw from the Q line down to the y equals x curve at xb. Now we're ready to determine the number of stages. So starting at xd, we move horizontally to the equilibrium curve, and then down to the upper operating line. Back to the equilibrium curve, down to the operating line. And we continue to do this back and forth until we reach the point where we cross over from the upper operating line to the lower. We can see here that we've now stepped off 1, 2, 3, 4, 5 stages, and so our feed stage would be in the 5th stage. Now we're going to operate off the lower operating line to finish out the distillation. We go to the equilibrium curve, lower operating line, and repeat back and forth until eventually we cross over to the composition that we want at xb. So if you count all the stages, we're feeding at the 5th, and then we have 6, 7, 8, 9 stages below the feed stage, or total of 9 stages, 4 stages below the feed stage, and that would be the design of our distillation column. Let's take a look at a similar design, except now our liquid feed is at its bubble point. So our Q line is now vertical. It intersects y equals x at ZF. And we choose a similar slope as previous, and now we can start stepping off our stages from x sub d at the top down to x sub b at the bottom. Here you'll notice that we cross over from the upper operating line to the lower operating line at stage equal to 3, and then we finally reach our bottom composition at xb after 7 stages. Here we take a look at what would we get at different reflux ratios. Again, we would have a feed coming in at 0.5. In this case, my Q is 0.5, so it's halfway between a liquid at its bubble point and a vapor at its dew point temperature. As you can look at the difference between the upper operating lines at various values of reflux, we see that increasing the reflux ratio draws the upper operating line closer and closer to the y versus x curve. And if you were going to step off stages, you would also see that the higher the reflux ratio, the fewer the number of stages you would need to design your column. There is a minimum reflux ratio that is achievable in a column. In this case, we will look at a system like before, but let's draw our upper operating line where that intersects the Q line right at the equilibrium curve. And this is the case where R is equal to 1. If you try to step off stages on the upper part of the column, you will find that you would get pinched in right at that intersection point. And so this is the minimum number for the reflux ratio, which actually would require an infinite number of stages in order to achieve this. And so you cannot go to a value of reflux ratio less than that minimum value. And that would be determined based on the intersection of the Q line and the equilibrium curve. The overall design procedure would be to first perform a material balance on the column so that you can determine the values of the distillate flow, bottoms flow, the composition of the distillate, and composition of the bottom. Then you would need a vapor-liquid equilibrium curve, either from experimental data or an appropriate model. We would plot a 45-degree line, y equals x, on our process. We would plot our Q line, and then determine the minimum reflux ratio as described in the previous slide. And then we would increase that reflux ratio to a desired amount. We would connect the lower operating line to the point where the upper operating line and Q line intersect. And then we would step off our stages from top to bottom, and from there that would determine the feed stage and total number of stages. And this completes the way of graphically designing a distillation column.